Recording is rolling. It is Tuesday, January 28th. I have a spring oscillation lab lined up for you guys. So you guys have this lab page, yeah, you guys have some springs. You guys have box of lab weights. You guys got meter sticks and stopwatches. You can do this whole thing with those things, right? So I want to lead into this. Right, here's a good, probably handy formula that's going to be for part of the lab today. Right, time period is 2 pi squared over k. Okay, kind of remember that. Right, this sure does look a lot like your guys' time period of oscillation for a pendulum swinging back and forth, except for a pendulum. Guys, how is this different for a pendulum? It was what over what here inside the square root? It's L over G, right? L over G, right? And then, okay, so for a mass on a spring, which you guys are about to do today, okay, really similar looking structure. Well, it's the same structure, right? Really similar looking formula, okay? So now the pendulum version, I had you guys figure this out from scratch. This version, I'm giving this ahead of time, and you can use this to what's this up. Right, kind of how this leads in. Now it's going to take me a while to build up to this. It's going to take me a few minutes, but if you can measure, well, if you know what mass you're working with, like this right here is 0.1 kilograms, and you could measure the time of oscillation, do you think you could, in principle, calculate the spring constant? Right. So hold on to that idea because you'll see that today. Right. But before we get to that, I have a few posters I want to review with you guys, including this one, because I was looking at this lab tape there. Well, yeah, I pulled this out of my files from last year, and yeah, there might be a couple things I would tweak on it if I did that from scratch. But one of them was, I didn't actually give a space for this type graph. So I want to put together a couple of these graphs with you guys in the first few minutes of class today. So we're going to take a few minutes. We're not quite at the lab yet, but I just want to look at this oscillation. Now, this could definitely apply to your guys' setup today, because here, you guys know your setup is you got a mass on a spring. Maybe you pull it down, let it go, it starts to oscillate. Wow, 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 wow. Right? Actually, I'll draw that right here. So you guys can write this in your notes. So it's just extra notes right here. Right, we're going to draw a couple graphs. So you guys got a spring. It's just hanging right there. Right, hang it there. Right. Then you hang a lab weight on it. Right. All right. Or let's say that's the equilibrium. So if it's at rest, it looks like right there. Okay. And then maybe you give it a little pull, maybe like 1 centimeter, 2 centimeter, whatever. Right. It starts to oscillate up and down. Wow, 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 wow. Right. Something like that. Okay. Now, how much time does it take to oscillate up and down? Depends on what mass this is and what spring constants in the spring. Okay, that's what this expression is saying right here. That's that relationship. Okay. But for the purpose of these graphs that I'm about to put together with you guys, that you guys are putting in your notes, I'm just going to give you guys two quantities, and it's not the mass, it's not the spring constant. I want to tell you guys the amplitude that I pull down. Let's say I pull down like 1 centimeter. No, let's do 5 centimeters. Looks more exciting number. So let's say I pull 5 centimeters amplitude. Now let it go. Okay. Hey guys, if I pull down 5 centimeters, it goes down 5 centimeters, and then this distance right here. Do you guys see that? This distance right here could be amplitude 5 centimeters. Okay. When it's oscillating back and forth, do you think it's going to race back through the equilibrium point and go up? How far? Guys, how far above the equilibrium point is it going to go? Another 5 centimeters. So between the highest point and the lowest point, guys, what's that total height change? 10 centimeters. Do you see that? That's the difference between amplitude and total wave height, right? Like if you thought about this being like a periodic wave, right? Yeah. So from the bottom to the top is a total of 10, but the amplitude is just relative to the equilibrium point, which is 5 centimeters. Right? And the other value I'm going to give you is time period. Let's say this whole thing from from one point back to the original point takes 4 seconds. Okay, 4 seconds. Okay, so that could be from where I release it. Maybe it takes 2 seconds to go up and then 2 seconds to come back down. So it's oscillating back and forth really slow. Maybe it's not a very stiff spring, or it's not a very big mass, or some combination. So it's going like, that might be even too fast because it takes 4 seconds to cycle back and forth. You guys get that? Okay. Now, just from that alone, we can put together these oscillation graphs, which we're going to do right now. Okay. Now, I just want to do displacement versus time and velocity versus time graphs with you guys. So you guys set up a couple of sideways t-looking axes, right, sets of axes. You guys that, right? And let's see if you guys are really following where I'm trying to go with this thought. Because what variable goes on this horizontal axis? What's ticking along here? Time. Aha, time. Right. I'm really just going to reconstruct these graphs, right? Okay. We're going to come up with equations. You guys see these red equations, right? So what is this graph's going to look like? And what are these red equations going to be to describe this graph for exactly these? Remember, all I gave you was two numbers. I just told you the amplitude and the time period. Right? We can make the whole thing into yeah. So time in seconds is tick along, tick tock. That's also going to be true for this one. Okay? And we're going to say how far has this mass moved in centimeters? How far in centimeters? And then how fast in centimeters per second? It's going to take me a few minutes to get to that point, but we'll build up there. Okay? Right, so you guys got your axes outlined. You guys got your axes labeled, variable, unit. Okay. All right. So let's do two complete cycles. We'll do two complete cycles. Okay. So if it was one complete cycle, that's how much time again? 4 seconds? Or it takes 4 seconds to cycle. So I'll put 4 seconds right about here. So 4, and then the unit's already that is seconds. Okay. And let's go all the way up to 8 seconds then, because that would be 2 cycles, wouldn't it? And then when we get down to this velocity graph, it's going to be that same story. 4 seconds, 8 seconds. Maybe I should divvy that into 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. All right, all good? Okay. And then, how high up should I label this vertical axis? How many centimeters would be a good number? 5 centimeters. 5 centimeters, right? Here's the equilibrium is at 0, and it could go all the way to -5. Right? Again, guys, what's the difference between +5 and -5? It's 10. Yeah, it's 10, right? 5 minus -5 is 10. Right? All right. Okay. I'm going to give you guys 1 point on the graph. I'm going to see if you can create the whole graph just from this 1 point. You guys ready? Okay. Here's the point. Right here. Bam. So I'm giving you that point. I'm saying at the point that I release it, it's 5 centimeters displacement from the equilibrium. Then I let it go. And it starts to oscillate. It's going to make a graph, right? Go ahead. Make the X versus T graph right there. I'll walk around the classroom, see who's able to get that. Oh. Yeah. Okay. Yeah, so we're not quite at the lab yet. I'm just doing this extra set of graphs with you guys. Okay, this is just for your notes. Okay, so we're just doing notes graphs right now. I'll walk you guys through the lab tables in a few minutes. I bet. All right. Yeah, see, Alexander's got it. See, got it. All right. Yeah. Okay. Elise got it. Olivia's got it. Okay. Ooh, yeah. I think some of you guys are getting there. All right. What you guys said was, right. So get that starting point right there. So as soon as I let it go, I start timing. Okay, so that's at time 0, of course, right? Time 0 here. Okay. Well, it takes 4 seconds to cycle. So after 4 seconds have elapsed, it's back exactly where it started, right? Okay. And how about at the 2 second mark? Guys, at 2 seconds, where is it? 5 centimeters on the other side, right? And, what's going on at the 1 second and the 3 second mark? Is it passing through the equilibrium point at both of those times? Okay, now, traveling different directions, but it's passing through this equilibrium point so it takes 1 second to get to the equilibrium, then 1 second it overshoots it, then it takes another second to go back to the equilibrium, and then the 4th second gets back to where it started, right? Now, this is like one of these, well, actually it's going to be a cosine curve, isn't it? Because it starts at, what do you call it, sine or cosine? You could actually describe this with either sine or cosine, because they're the same shape, they shift around a little bit. But cosine's a better option because it starts at the amplitude point, right? Got an intercept there, right? How about this? Let's do another cycle. Give you 5 seconds, 6 seconds, 7 seconds, 8 seconds. There's 2 full cycles right there, right? And if you let this go, maybe this could go for, I don't know, dozens of cycles. Right? Keep on. Right, let's come up with an equation. So say x equals, or you can say x of t if you want it to look like a function. That's okay too. X of t equals. Okay. All right. Now I'm going to use this poster as a model. You guys see this red formula right here? Okay. And now we have some numbers because, of course, on my poster, it's just variables, but I give you guys a couple of numbers. So x equals what? Guys, what's the first number I want to write right here? Yeah, 5 centimeters. So I got 5, so centimeters, okay, multiplied by, because that's where the amplitude goes, 5 centimeters, okay. Yep, this definitely looks like a cosine curve, so let's choose cosine, okay. And then, well, now we're running into stuff that I talked about yesterday, but I haven't reminded you guys about today yet. Guess this is omega t, right? Okay, well, I know what t is. That's just your variable. It's just time taken along. What does this omega represent again? It's not angular, don't say angular velocity, because that was a few weeks ago. This is angular, what does F stand for? Free, frequency. Yeah, frequency, right? So the omega is the angular frequency. So if you just take your regular frequency and multiply by 2 pi, then it helps you construct this graph because a sine or a cosine function cycles how many radians? Guys, how many radians are there all the way around the circle? 2 pi. That's where that comes from. And I'll show you guys as we start to put this together. This will make more sense. Right? Okay, so let's get, well, what is the frequency? Well, I didn't quite tell you that, but I did tell you what that you can use to determine frequency. Guys, frequency is the reciprocal of what? So do I have a poster for that? Oh, it's right here. It's right here. You guys remember this? You guys remember this? Right? Frequency, time period are reciprocals of each other. Right? And then once you know the regular frequency, multiplied by 2 pi, you get this angular frequency. Right? So this is a really handy poster for what we're trying to figure out right now. Right? So guys, if it takes 4 seconds to cycle, then what's the frequency equal to? 0.25 hertz. 0.25 hertz. Like a quarter of a hertz. Okay. All right, guys. Here, let's do the auditory version. So if you heard this, is that about 1 cycle per second? Right. So I would say that's a frequency of 1 hertz, and the time period between beats would be 1 second. 1 over 1 is 1. Okay. Because what if I do this? Is that approximately 4 beats per second? Could you call that a frequency of 4 hertz? And what's the time period between beats? A quarter of a second, right? Right. Which is the exact reverse of the example that we're doing here. So the example that you guys just wrote in your notes is more like this. Right? Okay, so like every 4 seconds there'd be a beat, right? Okay. And then take reciprocal. Now the frequency is a quarter of a hertz. Okay. So reciprocals, right? Okay. Now, if you want to make that angular frequency, omega, for this graph, what do you multiply by again? 2 pi, okay, because that'll make it consistent with a sine or a cosine. Okay. So let's do 2 pi times 0.25. Now, if you want to leave it in terms of pi, like as a fraction, that's okay. I'm going to write, does this look like pi over 2? If you want to write pi over 2, here, I'll do it both ways. Let's do pi over 2. Now the unit still hertz. Or if you like, as a decimal, it's like 1.5708 hertz. So those are about the same thing. Okay. All right, so there you go. All right, you guys good? Right. Now we can go finally finish this equation. So I got x equal, okay, I got 5 centimeters times cosine. And what goes right here inside the cosine? Is it pi over 2 hertz times however much time has elapsed in seconds t? Okay, right? And then in place of this t, you can put 1 second, 2 seconds, 3, however many seconds have passed. You see that? Am I sure? Is that really true? Let's put this to the test. I'm making the claim this is true. We went through all this. We got time period, made that frequency, made angular frequency, and something with cosine. Okay. Let's see. This equation should describe this graph. Let's pick a couple of points. How about at 3 seconds and at 4 seconds? You guys see that? Right. Guys, if I plug in 3 for this time, for 3 seconds, what should the calculator tell me? Yeah, 0. Right, if I plug in 3, I should get 0. What if I plug in 4? What should I get if I plug in 4? Yeah, positive 5, right? And actually, you can pick any time and plug it into this t, and this equation should be consistent. Now, one more detail right before I go plugging this in is notice this is inside a cosine function. So, guys, the only way for this to actually work in your calculator is your calculator has to be programmed in what? Degrees or radians? Has to be in radians. If it's in degrees, it's no good. So on this calculator, I go to, there's a button up here, it says DRG. I click that. I can change from degrees to radians. Right. Okay. Now my calculator's in radians. So now it will, or it should align. Let's see if it does. So 5 for 5 centimeters times cosine of, okay, I got I got a pi over 2 is my angular frequency in hertz, multiplied by, let's plug in 3 seconds right here. Right? Right. And again, when I hit enter, I should get what again for 3 seconds? Should get 0. Let's see if this is 0. Hey, it's 0. It's 0. All right. How about if I scroll up, scroll over, and where the 3 used to be, I'm going to put a 4 for 4 seconds. Now when I hit enter, I should get what again? Yeah, 5 as in 5 centimeters. Hey, it is 5. Look at that. Is that? Yeah, again, you can pick any point. You guys see how this equation definitely describes that curve? Right. I know we did a couple points. You could do any point in a little line. All right. All right. So one good question might be, I wonder what's the maximum speed of this mass going through the equilibrium. Oh, I meant to ask you guys. Oops, I gave it away. Guys, what location? See if you caught it. What location would the maximum speed be? At the top, at the bottom, or right in the middle? How about right in the middle? Yeah, right when it's passing through the equilibrium point. Shoo, 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 shoo. Now it's always speeding up and slowing down, but so maximum speed there. Okay. Now notice this amplitude has nothing to do with how much time. Do you guys notice that? The amplitude has nothing to do with how much time it takes to cycle, but it is related to the maximum speed. I bet the more you pull it, the faster it goes through the middle, right? So I'm gonna consult this poster again. I'm just gonna work off this model right here. Now, yesterday I was walking you guys through this thought process where it comes from. If you've taken calculus or you take calculus, you can derive this from scratch. Right? We're just gonna take this as a given and work with it. Right? So going from position to velocity, that's our rate change with respect to time. Cosine changes to negative sine. Everything else stays in place. The omega t stays in place. The amplitude stays in place. But also an angular frequency comes out. You guys see that? It gets multiplied. So let's make that equation. So let's go velocity equals, right? And okay, and it's going to be negative. So got a negative in the mix. Now amplitude times angular frequency. Well, that's this right here. Amplitude was 5 centimeters. Angular frequency was pi over 2 hertz. Put it all together. I'm getting, here, I'm just going to go with the decimal version of this. Negative 7.8540. That'd be centimeters per second. Right? Multiplied by sine of, and then everything else just follows. So I got pi over 2 hertz. Pi over 2 hertz times however much time t has elapsed, as t is the variable. Right? You can plug in however much time. Right? So that equation right there, this equation should describe, well, the graph we're about to draw. Okay, you guys get that? Okay. Okay. Now, before I draw the graph, who can look at that equation and tell me what is the maximum speed? You guys remember that question? What is the maximum speed? What is the maximum speed according to that equation you just wrote? Yep, 7.85 centimeters per second. That's it. Okay. Because I know sine of something, and cosine for that matter, can max out at 1 and minimize at -1. So this, guys, this bit right here, the sine of whatever is bounded between -1 and 1. Right? Is that true? Like on a unit circle, you can only go as high or as low as 1 or -1. So if you max that out, multiply by 7.85, you can go as fast as 7.85 centimeters per second. That's maximum speed. Okay. All right, so what points can I go on this graph? Here, go ahead, draw that graph. What do you think that graph looks like? All right, I'll walk around the room, see who's getting that graph right there. Give you guys a head start. So, like normal, all right, you guys can stay a step ahead of me. That's a good sign. If you guys can put together that graph before I show it to you, that's a good sign you know what's going on in this class. Velocity versus time. What's that going to look like? All right. See, some of you guys are kind of in the right direction. Okay. So, you guys know it's something to do with a sine curve, and also it's negative. Don't forget the negative. I think some of you guys missed the negative, but those are pretty close. Okay. Well, here's my model right here. Does it look like this? Guys, look like this? Right? So it starts out, it does start at rest. That would be consistent with this x versus t. Okay. So at time 0, it's 0 centimeters per second. Because remember, I pulled the mass back, some amplitude, and I let it go. As soon as I let it go, I started the stopwatch. So at the point I let it go, it's not quite moving yet. Right? And then it's gonna, well, upside down sine curve is negative, right? It's gonna go to or oh, actually, here, let me get some other zeros on the board. You guys remember yesterday I told you the slope of x versus t tells you the coordinate of v versus t, and same thing back in like August, September, same story. Okay, so every time you're on a hilltop or every time you're at the bottom of a valley, isn't that zero slope, right? Which tells you 0 centimeters per second meter speed. So that's at the 2 second mark, at the 4 second mark, at the 6 second mark, and at the 8 second mark. So there's 5 points on the graph. You guys see 1, 2, 3, 4, 5 points. Those are all points where it's, I guess it would really be turning around is what it would be doing. A zero instantaneous velocity. You point a radar gun at it, reads zero. Okay. Okay. How about the rest of this? Is this gonna go like this right here? And then oink. All right. So I'm filling in the graph right here. Right. I want to throw one more detail in this graph, which is what is the amplitude? All right. So guys, what is this number right here? 7.85. That'd be centimeters per second. You got the unit embedded there, and this would be negative 7.85 centimeters per second. Okay. All right. So you guys good with oscillation graphs? You guys put those together? All right. Everybody good? Everybody good? All right. All right. So again, that's just for your notes. Let's be moving on towards this lab then. All right. So got that. Okay. Now, yeah, I did copy a lab that I found in my binder, but I think if I redesigned it, because you guys have sort of a split table. You guys got this table here and this table here. If I made this from scratch, I'd probably just put it all in one table. So that's okay. You guys can use the same masses over and over. That's all right. Okay. And you guys remember for your pendulum lab last week, had you guys linearize a graph? So you have to manipulate the axes. Right? We've done that a few times in class, right? You're going to see that today too. Now, so yeah, I kind of gave you guys maybe too much here. Maybe I should have challenged you guys a little bit, right? But I told you on this axis put mass, on this axis put t squared or 2 pi quantity squared. Right? I think I was setting these up so that the slope is equal to the spring constant. Okay. Now in my poster version, I linearized it a different way, but same concept that you can linearize a graph, get the slope really easy, make an equation really easy. Right? I want to remind you guys of this too, because this is going to show up today. So guys, say I take a weight. And I'm looking at the spring right here that's just hanging at rest, nothing really going on. And I hook it right there on that spring, right? And then I drop it, right? And it's going to overshoot the equilibrium and go to some max stretch position. You guys see that? Okay. And it's going to maybe oscillate back and forth a few times, and then it eventually reaches equilibrium and come to rest. Okay. Now that equilibrium position, guys, how do you find equilibrium again in physics? What's the framework? The sum of what goes to what? Force goes to zero. Yeah. So here's the sum of force goes to zero. I got two force, weight and spring force. Hooke's law, right? Rearrange it, solve for x equilibrium. All right. The more weight, the more it stretches. The stiffer the spring, the less it stretches. That makes sense. Okay. What's the framework for maximum stretch distance? Conservation of energy. That's the setup here. A little bit different setup, right? So you can solve for x max, right? Now, if you look at the end results, if I compare these two, here's what I want you guys to see: is they look almost identical, except they're off by a factor of what? 2, right? So for example, if this stretched out to 7 centimeters, this is probably going to stretch out to pretty close to how far? 14, right? About so this could be 7, this could be 14, maybe. All right. So look for something like that. All right, let's look at your guys's lab page here. Okay, so you got this set up. You hang some spring. Now you guys have different type springs. Some will work with heavier weights, some with smaller weights. So, all right, individual basis here. Okay. So the table on the left side of this is more geared towards Hooke's law, right? I'll run an example with you guys. Now, guys, do not copy the numbers that I'm going to do right now. Are you guys going to copy the numbers I'm doing right now? No, because I'm just making something up. All right. All right. Let's say you have, here, let's do this lab weight. Guys, 100 grams. 100 grams, how many kilograms is that? Is that 0.1 kilograms? Right. So I'm going to put 0.1 kilograms here, if this is it. And if I want to do the oscillation at the same time, here on the right side, I'll also copy this here because I'll use this later too for the oscillation version. Okay. Right. X max. Suppose I drop this, and let's say it drops. Let's use the same numbers I just said a minute ago. Let's do 14 centimeters. Okay. So I measure 14 centimeters. It drops X max, and I let it settle after a while, and it settles at 7 centimeters. You guys get that? Should be pretty close to a 2-to-1 ratio. But you guys can see empirically if I'm telling you the truth. See how true that is. Right? Right. Force from the scale. Okay, now this one here, we're gonna do this a little bit different. When I originally designed it, I was like, okay, well, you could measure the weight by hanging it from a spring scale. Let's not do that. Let's just say, you said it's 0.1 kilograms. Guys, how much does this weigh approximately in newtons if I pick it up? How much force is that? 1 Newton. Yeah, 1 Newton. Okay. You can say 0.98, but I'm just going to call it 1 Newton. Okay, so let's just do it that way. So this is 1 Newton. Is that right? Anything bigger than this is more than 1 Newton. Anything smaller than this is less than 1 Newton. Okay. Right. Hooke's law. You guys remember F equals kx? So, you have F, the force at equilibrium. That's just the weight, which is 1 Newton. And the x, now this is x equilibrium, so like 7 centimeters. So divided by 7. This could be 0.14 Newton per centimeter. Or here's what I really should have done, because I didn't realize this until we got going on this today. I should really have this in Newton per meter. So let me add another column over here, K. And I'll put this in Newton per meter, right, for comparison. Well, guys, how many centimeters in a meter? 100. So if you do the conversion, it works out to about 14. Let's call it about 14. It's like 14.3 is what it is, Newton per meter. Okay, that's if you happen to get that exact set of numbers. That's how those numbers would play out. Okay, some measurements, some calculations. Yes, yeah. Okay. All right, now let's look at the oscillation version with the stopwatch, because the left table is you measure with the meter stick or a ruler. Right. This table on the right side, I want you guys to time some oscillations. So we do a little sneaky calculation off screen here. I'm gonna do. I just want to make sure my numbers work out. Okay. Let's say you let 10 oscillations go by, and it took 5.3 seconds. I'm just again making something up. Right. Suppose that 10 oscillations is 5.3 seconds. How much time would it be for one oscillation? 0.53 seconds. Would that be true? Right. That's it. Right. And then, could you calculate K, the spring constant, from that oscillation method? Now, that's where this comes into play. Okay. In your pendulum version, I had you figure this out from scratch, but the oscillation spring version, I'm giving this formula to you. I'm saying, if you know this M, you know this T, could you solve for this K? Could you guys do that? Right. Now, I did actually do that for you already, and I put it right down here. So I'm going to try this out. So open parenthesis, 2 pi, close parenthesis squared, times the mass, which is 0.1 kilogram, divided by T squared, which is 0.53 seconds, and square that, right? I'm getting the K of 14.05 Newton per meter. Okay? And then I have a manipulated axis column here to help make this graph. And then this graph, you can maybe use the slope and figure out the spring constant from the slope of the graph. Right? Right. All right. And if you do everything right, and you have ideal springs, and you have good measurements and good calculations, you guys see how the two spring constants pretty much align? Okay. I got 14 Newton per meter here and 14 Newton per meter here. Okay. As long as they're both in Newton per meter. Okay. All right. All right. So go ahead, get some data. You might only be able to do like 3 or 4 weights on some of these springs. Okay. So guys, you're using the same spring over and over. So you have the same spring constant. You guys get that? It's the same spring. What are you changing from trial to trial? You're changing the what? Yeah, the lab weight. Okay. Yeah, if you only have like 3 or 4, then that's okay. Some of the springs can only handle 3 or 4. If you keep a pretty good pace, I bet you can put the graphs together by the end of class, right? And then, guys, at the end of class today, hold on to this page, because on the flip side, there's a lab I want to do with you guys tomorrow, which involves calculating the speed of sound using a tuning fork.